recording here. Okay, so once again, in section 5.1, you learned about eigenvalues and eigenvectors, and you had a problem where you were given an eigenvalue and you had to find a basis for the corresponding eigenspace. And then you saw a geometric interpretation of that eigenspace through a figure in a beautiful figure in the textbook. So in section 5.1, they introduced eigenvalues and eigenvectors, and you got a feel for what they are. And in the problems in section 5.1, you are given the eigenvalues, and then you can, find the eigenspaces or eigenvectors, and there are a lot of little problems that'll test your definition, your understanding of what an eigenvector and eigenvalue is. But now in section 5.2, we need to say to ourselves, okay, if we're given some square matrix A, how do we find the eigenvalues? We find the eigenvalues by solving what's called a characteristic equation. And I'm going to give you a moment to copy this example down, and then we'll talk about it. Okay, so, all right. So this is called the characteristic equation. If you take a square matrix A and subtract lambda times the identity matrix, form that matrix and take to the determinant. The determinant of a matrix will give you a number, right? So take the determinant of A minus lambda I, set it equal to 0. You can find the eigenvalues by solving the characteristic equation. And so this vector equation, A times X equals lambda X. And by the way, we're assuming also that the eigenvectors X, those eigenvectors are not equal to 0. So in the definition of an eigenvector eigenvalue, A times X equals lambda X, where the vector X is non-zero. And that definition is given in section 5.1. So we have to find the eigenvalues, the lambdas. We can do that by solving this characteristic equation. But you should see why it's true. Okay, a lot of times it might be just stated this result, but you should know why it's true. So what I'd like to do is go through a little proof with you, and it'll be a very instructive proof. So, okay, let's go to the next page. So again, our goal is we wish to find all scalars lambda such that A minus lambda times the identity times the vector X equals 0 has a non-trivial solution. Now I should say, let me just go back to the previous page. So you might wonder, well, gee, Dr. Duty, all you wrote down is this, that the determinant, one moment, the determinant of A minus lambda I equals 0. Okay, let me just get my thing here so I have it in front of me. I wrote down this characteristic equation, and then from there, I say, okay. In the proof, I say, all right, we wish to find all scalars such that A minus lambda I times the vector X equals 0. Find all scalars such that this matrix equation has a non-trivial solution X. Okay, well, where did that come from? Well, that came from this. That's true because remember what we're starting out with. A times X equals lambda times X, where X is not equal to 0. That's the definition of an eigenvector X and an eigenvector and a scalar eigenvalue lambda. So I should say definition of eigenvalue, comma, eigenvector. Now we can manipulate that matrix equation. Okay, on the right side, lambda times X can be written as lambda times the identity times X. And then we can bring lambda times the identity times X over on the left side so that A times X minus lambda times the identity X equals the 0 vector. And from there, on the left side, we can factor out the vector X. Factor it on the right side, of course. And so you end up with then, in parentheses, A minus lambda times the identity times the vector X equals the 0 vector, where the vector X is non-zero. And that's what we're trying to find. So when we're trying to find eigenvalues, okay, of this matrix equation here, it's equivalent to finding eigenvalues of this matrix equation. And that's why I said we wish to find all scalars lambda, all eigenvalues, such that A minus lambda I times the vector X equals the 0 vector. But the scalars have to be such that the vector X is a non-trivial solution to this matrix equation. Okay, because X is an eigenvector, and the eigenvector is not equal to 0. So far, are we good? Are there any questions? All right. All right. Matthew's good. Christy's good. Robin's good. So far, so good. All right. Well, now let's go ahead and try to solve. I mean, just so I have my matrix equation here, and if I wanted to solve for the eigenvector x, I could do it. I could do it. Well, I want to be a little bit careful. So anytime, okay, like you're accustomed to, if you have a square matrix A, and maybe well, I'll call it a square matrix C times a vector x equal to a vector B. If C is invertible, then the vector x would equal C inverse times B. Okay? So if we look at this matrix equation, A minus lambda I times x equals 0, and let's forget for a moment that x is an eigenvector. If we just had that matrix equation and we wanted to solve for x, if A minus lambda I, if that were invertible, then x would equal A minus lambda I inverse times the 0 vector, which is equal to the 0 vector. And that would only occur if A minus lambda I is invertible. That would only happen if A minus lambda I is invertible. Are we agreed on that? All right. So this means then, if I go to the next page, may I go to the next page? Are we good? Everybody good so far? Okay. All right. Well, that's Matthew is on the right track. Okay, hang on. Matthew's on the right track here. So, okay. Are there any other questions before? I want to make sure I'm pacing myself right. I have to remember, you all are copying this down. So, all right. One moment. Hey, Alan, I'm in class, so good to hear you. Good to hear you. I'll let you talk to Kurt. But maybe we can talk. We'll talk soon. Let you talk to Kurt though. All right. Thanks. Bye. Okay. Okay. So now, so let's if A minus lambda I is invertible, this means that the vector x equals 0. But we don't want that, do we? Because if the vector x equals the 0 vector, it's not an eigenvector. What we want is solution vectors x that are not 0. But if that's the case, then A minus lambda I cannot be invertible. It cannot be invertible. Okay, so this is called a proof by the contrapositive. I don't know if you've maybe seen this before, but if P implies Q, then not Q implies not P. Christy's seen it in discrete math. Well, that's what we're doing here. We have a statement P. Okay, Michelle, we have a statement P that implies Q. Well, this means that not P, which is sometimes we use a squiggly for not P. How many have seen the squiggly for not P? Like, how many have seen that notation? Okay, say yes. And actually, what I want here, all right, what I want actually is not Q, right? We call it negation. That's right. That's right. So not Q will then imply not P. So since we want to solve this matrix, equation, but we want eigenvectors. We want to find, to find the eigenvalues, x has to be an eigenvector. Well, for x to be an eigenvector, x cannot be equal to the zero vector. If x is not equal to the zero vector, then that means a minus lambda I is not invertible. But then if a minus lambda I is not invertible, then the determinant of a minus lambda I would have to equal 0 by the IMT. What's the IMT stand for? What's that abbreviation stand for? Think back to your textbook. Invertible matrix theorem. That's right, Solomon. And so now we've proven that we need to solve this characteristic equation. If we can solve that characteristic equation and find lambda values, they will be our eigenvalues. And then once we have the eigenvalues, we can go after the eigenvectors. We can find those. Okay? So are there any questions? Any questions on that at all? All right. Well, what I'm going to do, I'm going to bring up now the lay textbook, our textbook here. And I want to go into section 5.2 a little bit. I mean, there isn't a whole lot to the section, but we'll look at a few examples. Let me see. There was a chat question. Okay, well, yeah, and Sega, what this was just so you're going to, in section 5.2, in that section, you're going to be using this all the time, solving the characteristic equation, determinant of a minus lambda I equals 0, to find eigenvalues. And I wanted you to know why you're doing that, why it's true, why you can find the eigenvalues by solving that equation. And all right, so are there any other good questions? Okay, well, let me bring up the ebook. Okay, so in the ebook, let me make sure it's projecting. Yep, it is. So in the ebook, first example, hold on, let me get my little, they want you to find the eigenvalues of this 2 by 2 matrix. And so you first have to find A minus lambda I. You have to find that first. And they show you how to do that right there. So are there any steps on that highlighted portion? They take the, I mean, lambda times the identity would be lambda times the ones along the diagonal. And then you subtract you subtract the second matrix from the first, which you can do because they have the same row and column size. And now you just simply take the determinant of lambda minus I. And you know how to take the determinant of a 2 by 2. Okay, so the determinant will become a polynomial in lambda. And then, like in this case, that polynomial, and again, you don't have to copy this. This is just, I'm giving you a little guided tour of the few examples in section 5.2. You can factor that, and so your eigenvalues, the characteristic of the determinant of A minus lambda I becomes what we call a characteristic polynomial. It's when you set that polynomial equal to 0 that you have the characteristic equation. But clearly, lambda squared plus 4 lambda minus 21 factors into lambda minus 3 and lambda plus 7. And so you set that equal to 0, and you have your two eigenvalues. Okay, and that's how you get your eigenvalues. Okay, are there any questions on that particular one? One moment, let me. Okay, good. Saget's very comfortable now. Good. Okay, good. Christy's good. Wonderful. Okay, well, so let's go forward a little bit here. Let's go forward here. I'll just kind of point out some highlights here. Okay, they extend the invertible matrix theorem a little bit more. All right, so some interesting things here or there. And here's another example. Example 3. Oh, they have a 4 by 4 matrix here. And they want you to find the characteristic equation of this 4 by 4 matrix. So naturally, they reference this theorem above, but I think you're aware that if you have a this matrix A, how do we classify that matrix? What kind of matrix is that? Okay, it's in echelon form. That's right, Solomon. And since it's a square matrix, it's in echelon form. And also, we would call it what kind of form? I mean, there's another word too we can use. If we focus on the, I don't know if I'll be able to do it well here, but if we focus, one moment. These zeros here in the matrix A form what it looks like to be a, well, that looks like a little, what? The yellow highlighted zeros. What does it resemble in geometry? A triangle. That's right. It's a triangle. So this matrix A is in triangular form, and it's actually in lower triangular form. Wait, hold on. The zeros are in the bottom. So let's just say triangular form, okay? Well, is it easy to take the determinant of a matrix in triangular form using cofactor expansion? It is. All you need to do, and you've learned this firsthand, is if you take the determinant of a matrix and it's in triangular form, the determinant is just the product of the diagonal entries of the determinant. So the determinant of A minus lambda I, and they write A minus lambda I here, the determinant is just the product of the diagonal entries. And that gets you the characteristic equation. Okay, that gets you the characteristic of, well, that gets you your characteristic polynomial. And then the characteristic polynomial can be, through algebra, written out to be a characteristic equation. And the eigenvalues, by the way, what are the eigenvalues going to be for this example 3? Good. Good, Solomon. 5, 3, 5, and 1. And we say that because, you know, I mean, it's in factored form here on the left, like they have it in factored form. If you set that factored form, I'm talking like right here. If you set this factored form here in equal to 0, the eigenvalues are going to be 5, 3, 5, and 1. And actually, the eigenvalue 5 has what we call multiplicity 2 because it occurs twice. The eigenvalues 3 and 1 each have multiplicity 1. But what you'll notice when you work on your homework is that when you have an answer, and they're going to ask you to find characteristic polynomials of these, you know, of the determinant, which is just the determinant of A minus lambda I. But they actually want the answers written out, expanded out, like you see here. Okay, they want the answer that way. They're not going to, even if you can write the answer in factored form, they're going to want the answer written out, like where you do the algebra and actually get the polynomial. They don't want the polynomial in factored form. They want it like a polynomial, you know, in non-factored form, which is kind of interesting to me because factored, we learn that factors are, we've always want to factor these polynomials, you know. So, but at any rate, that's how you have to get your answer. And well, yeah. Christy, you're good, right? It's no big deal. You just gotta, you know, multiply things out. No big deal, but right. And the factoring is the hard part. And now mistakes can happen. That's right. They can happen, so you have to be careful. That's right. Right. Now, another thing too that is mentioned, let me just see here. In example 4, they say find the characteristic polynomial of this 6th degree polynomial. So it can be factored. It can be factored, and then you get your eigenvalues. And they talk about these multiplicities. The eigenvalue 0 has multiplicity 4. Eigenvalue 1 has multiplicity, 6 has multiplicity 1. Eigenvalue -2, multiplicity 1. I think in the homework, how many remember having polynomials that can't be nicely factored like this? How many remember that maybe in in their pre-calculus, where you had to use like the rational root theorem to find the rational roots, and then, you know, Solomon remembers and Devahar. Okay, so I think in the online homework, I don't think you're going to have to worry about that. Okay. Okay, but of course, you know, well, you know, you're welcome, Matthew. But you know, if you ever had to find the roots, you know, you could always, well, you could. Let's just, you know, hopefully you won't have. Their focus is on you learning the linear algebra, and they know you could factor the polynomial if you wanted to. Okay, let's move on here. Giving a little guided tour here. Okay, let me just see here. Okay, now they haven't talked about complex eigenvalues. Notice they have a little thing here where they mention complex eigenvalues. That's going to be talked about in section 5.5. So complex eigenvalues, we're gonna get to that in this coming Tuesday's class. We're going to get into that. That's section 5.5. What you're going to see in you know, sections 5.2 and 5.3 is just real eigenvalues. And okay, all right. So let me just see here. Now, the book also talks about something called similarity. Similarity. Okay, and we say that a matrix A is similar to a matrix B if there's an invertible matrix P such that P inverse times A times P equals the matrix B, or equivalently, A equals P times B times P inverse. Okay, this is called matrix A being similar to a matrix B, and it's actually a very important concept for what you're going to learn actually in section 5.3. So a matrix A is similar to a matrix B if the matrix A is equal to P times B times P inverse. P would be an invertible matrix. And incidentally, this theorem 4 says if two matrices are similar, then they have the same characteristic polynomial and hence the same eigenvalues. They actually prove that. They actually prove that here in this proof here. They prove this theorem, and I think it's easier just to kind of look at the theorem with your own eyes instead of me narrating it completely. But you know, they start off with the b minus. I mean, they want to show that the determinant of b minus lambda I equals the determinant of a minus lambda I, right? Because if a and b are similar, then if the characteristic polynomials would have to be the same, and that means the determinant of b minus lambda I equals the determinant of a minus lambda I. So what they do is they start off with b minus lambda I. Okay, they start off with that, and then they substitute in. Hold on here. I don't want to highlight too much. They substitute in for b P inverse times A times P, because they're saying that B is similar to A, so B equals P inverse times A times P, and then they write the identity as P inverse times P. That's kind of clever. And then they factor here, they factor a P inverse out from the left side of both those matrix products. And so you get P inverse times AP minus lambda P. And then they factor a P out from the right side of this. They factor a P out from the right side. And so you get P inverse times A minus lambda I times P. Then they take the determinant of B minus lambda I. okay, right here. And the determinant of B minus lambda I the determinant is the determinant of P inverse times A minus lambda I. Well, it's the determinant of the product P inverse times A minus lambda I times P. But then the determinant, we know the determinant of the product of two matrices is the product of the determinants, and that's what they use here. But remember, the determinant of P inverse is equal to 1 over the determinant of P. How many maybe recall that? The determinant of P inverse is equal to 1 over the determinant of P. Yes, Solomon remembers that. Christy, okay, absolutely. And that, I'm sure it came up in the homework. Well, I know it came up in the homework. So, therefore, in this 2 here, in that 2 there, the determinant of P inverse times the determinant of P is just equal to the determinant of I, which is 1. And so there you go. They solved it. Are there any questions on that? They've proven theorem 4. And you'll have to do some of these kind of things in your homework. They'll have some conceptual questions where you have to do that kind of thing. Multiple choice mostly. But are there any questions on that? Uh-oh, did my thing disappear on me? Hold on, let me bring it back. One moment. I don't know what it's doing. Hold on here now. I got the book. One moment. I'm going to get the book back. I got to get the book back. One moment, class. I don't know what happened here. Hold on. Well, are we good? I don't know. I think what happened is it just went blank after I went. Everybody's good? Is everybody okay? Everybody saw the whole proof? Matthew's good? Okay, Robin's good. Christy, wonderful, wonderful. Okay, well, that's really what section 5.2 is about. That's really what it's about. Let me just see one thing here. I still want to bring up that book. So let me bring it up again. Hold on here. One moment. Let me just get it again. I want to bring that section up again real quick. Must have a timeout feature or something. I don't know. Something I wanted to bring up here. Okay, one moment. Okay. There's also, they talk about applications to dynamical systems. And this is something that is of importance to us. Eigenvalues, this is again section 5.2. Eigenvalues and eigenvectors hold the key to the discrete evolution of a dynamical system, as mentioned in the chapter introduction. So for instance, you're going to see later on, and you'll have a MATLAB project on it or MATLAB assignment, that you can determine if a species is going to, if it's going to survive or not using eigenvalues and eigenvectors. You can determine the evolution of a system. You can determine what will eventually happen to the species. And you know, right now, but I'm just saying that it's absolutely beautiful. And they talk a little bit here in example 5 about, they give a matrix A. Notice what's true about the columns of the matrix A. What's true about the columns of the in example 5? Okay, you'll notice they sum to 1. Okay, so it's a stochastic matrix. Stochastic matrix. And they want to analyze the long-term behavior of the dynamical system, okay, where your initial population distribution is 0.6 and 0.4. Oh, didn't we do this? Didn't we do this very kind of question in section 4.9? Didn't we have an example with this exact matrix A and this exact initial population distribution? Absolutely. 60% of people living in the city, 40% of people living in the suburbs. That's right. Solomon remembers. And so we learned that eventually, over time, if this is your migration matrix A, if this is your migration matrix A, then over time, we learned that eventually, after many, many years, 37.5% of the people of the people in that region will live in the city, and 62.5% of people will live in the suburbs. Now, we did that using concepts from section 4.9, but we can use eigenvectors and eigenvalues as well to arrive to the same conclusion. That's right. That's right. So look at how they do this. Look at how they do this. The first thing is to find the eigenvalues of A and a basis for each eigenspace. So they find the eigenvalues using the characteristic equation. Oh, this here you can't factor, so they're going to use quadratic formula. That's not too bad, right, everybody? Quadratic formula. That's right, Matthew. That's right. That's not too bad, quadratic formula. Okay, so, all right. They get the eigenvalues of 1 and 0.92. And then what they do is they find the corresponding eigenvectors. And you know how to find eigenvectors corresponding to eigenvalues. We did that in an example of that in the last class. Okay, so what they do is they have V1 and V2, the eigenvectors, and then what they do is they write the initial vector x naught, x sub 0, in terms of V1 and V2, which you can do because the V1 and V2, those two eigenvectors, form a basis for R squared, which means any vector in R2 can be written as a linear combination of those basis vectors. Okay. So, all right, they proceed forward. So x sub 0, which is the 0.60, 0.40 vector, 60% of people living in the suburbs, 60% of people living in the city, 40% of people living in the suburbs. They write that as C1 times V1 plus C2 times V2, which you can do because V1 and V2 forms a basis if you just get a basis for R2. Okay. And then, all right, well, you can solve for C1 and C2. You can solve that vector equation, and when they do, they get that C1 equals 0.25 and C2 equals 0.225. Okay, so now you have C1 and C2, and but now they make a little comment here. They make a little comment. All right, x1 is equal to a times x sub 0. You know that from the last class when we talked about section 4.9. If we want the population distribution after 1 year in the city and the suburbs, we just take the initial distribution x naught and pre-multiply it by the migration matrix A. Okay, well, x naught, remember, was C1 V1 plus C2 V2. So A times x naught could be written as C1 AV1 plus C2 AV2. Okay, that's due to the linearity. Well, that's due to matrix properties. Okay, that's just due to matrix properties. Let me just write one thing down here. I'm just writing one thing down. One moment. One moment here. Yeah. So like A times, like for this. Let me just write this. So this first part here, C1 AV1. So A times, let me just, hold on here. Let me just kind of, I don't want too much to be here. Because let's just see here, one moment. Yeah, if you take C1 V1 and multiply it by A, that C1 can be factored out. Okay, that's a matrix property. So you get C1 AV1. And then if you multiply A times C2 V2, you'll get C2 times AV2 because the constant can be, that C2 scalar can be brought out in front. And so you'll get C1 times 1 V1 plus C2 times 0.92 V2. And that's because V1 and V2 are eigenvectors. AV1 equals lambda 1 times V1. Well, lambda 1 is 1, so that gets you C1 V1. Okay, maybe I'll hold on here. One moment. A times V1 just equals V1. That because A times V1 equals 1 times V1. V1's an eigenvector. Okay. Hold on here. This is fine. Okay, so A times V1 equals 1 times V1 because 1 is an eigenvalue and V1's an eigenvector, and that's the definition of eigenvectors. V2 and lambda 2 are V2 is an eigenvector, lambda 2 is an eigenvalue, hence A times V2 equals 0.92 times V2. That's by the definition of eigenvectors. So see, you can write x1 as a linear combination this way. And then you can repeat the process. X2 will equal A times X1. Okay, and you can replace the X1 with the C1 V1 plus C2 times 0.92 V2. And if you do that, okay, which they do there, well, what's going to happen? X2 will equal C1 V1 plus C2 times 0.92 squared V2. And in general, what's going to happen is, if you want to find the population distribution of the city and suburbs after k years, it's going to equal C1 times V1 plus C2 times 0.92 to the kth power times V2. Okay, so far we good? I mean, it might take a little time to absorb, but I'm trying to go slow. But hopefully, yeah, and you might have to look at it again, but hopefully I'm, making it a little bit, hopefully somewhat comfortable for you. Okay, okay. Well, all right. So now from equation 4, they put in C1 and C2, or I should say from this 4 here, they put in C1 and C2. Okay, and so this now gets you the xk, and if you let k go to infinity, if you let k go to infinity here in this vector equation 5, what happens to 0.9? What happens to this 0.92 to the kth power as k goes to infinity, as k gets large? What happens to that factor? I mean, take 0.92 on your calculator and raise it to the 50th power. Tell me what you get. 0.92 to the 50th power. So, yeah. So what I'm trying to say, and thank you, Mikkel. Thank you, Solomon. I'm focusing on 0.92 to the kth power. What does that equal as k goes to infinity? So we're trying to find out eventually what the population distribution will be in the city and the suburbs. That means we're letting k, k is the number of years, so we're letting k go to infinity. We're letting k be large. So this 0.92 to the kth power, what would that go to when k is large? So I'm saying if you want to see, to get an idea, take 0.92 on your calculator and raise it to like the 50th power. And what do you get? What do you get when you do that? So I hope more than Mikkel and Solomon know here. I might have to go to the whiteboard. Yeah, a number extremely close to 0, okay? So the point is, this factor, 0.9 to the kth power, goes to 0 as k goes to infinity. So what you're left with then is 0.125 times the vector 3, 5. I mean, and that's what you're left with. Okay, but let's make sure I'd like to have a few more people comfortable with this. Let me go to the next page so that you can, let me go to the next page. So what I'm trying to emphasize is this statement that is highlighted here, the entire thing. Hold on, I might have to remove it. One moment. So this explicit formula for x sub k gives the solution of that difference equation. As k goes to infinity, 0.92k tends to 0, and so you're left with just the first vector, 0.125 times the vector 3, 5, which is 0.73. So let me just hold on here. Hold on. I'm gonna have to do this. Hold on. Here's what I'm trying to say. Let me bring it up. I mean, we're good, but we're almost there. We're almost there. But I'm going to feel badly if you don't understand this. So let me just kind of write it out here. So x sub k equals 0.125 times the vector 3, 5. So this is taken from example 5 in your book. Okay. Plus we have 0.225 times 0.9 2 to the kth power times the vector 1, -1. Now this, what's going to happen? What's going to happen to this term? What does it go to as k approaches infinity? Has to go to 0. Good, good, good. So that means as k approaches infinity, the distribution of people living in the city and in the suburbs is going to approach in the limit 0.125 times the vector 3, 5, right, times v1. Exactly, Solomon. Times the first eigenvector. Okay. And this is going to equal 0.375, which is 37.5%, and 0.625. So what you've seen here then is that as eventually 37.5% of people will live in the city and 62.5% of people will live in the suburbs, which is the same result as we got with section 4.9. Okay, when 4.9, we solved this equation to get the steady state vector. I mean, this is the steady state vector, right? That's the steady state vector Q that we had in section 4.9. But in section 4.9, when we solved the for the steady state, okay, let me just check one thing here. I think we're good. I'm just checking one thing, making sure that we're good. Yes. One moment. Yeah. In section 4.9, we found the steady state vector by solving this matrix equation. A times Q equals Q. So section 4.9, you had that approach. Section 5.2, with eigenvectors and eigenvalues, you can get the same result using this approach. Okay, does everybody understand that? All right, excellent. So you can see the power of eigenvalues and eigenvectors. You can see the beauty. Are there any questions at all? Well, what's going to happen is in section, so of course for your homework and for the exam, section 4.9, you want to use the method from 4.9, this method, to get steady state vectors there. But then in section 5.2, you would use this method. But I don't, in section 5.2, I think there might be just one question in the homework dealing with that. Oh, yeah, more broadly, Mikkel, it's a good question. To be honest, Mikkel, I've seen both used in applications. In graduate school, we use this method a lot, the section 4.9 method, because you know, probably, well, but this method here is you know, well, I mean, at least in my field, I've seen it used. I've seen section 4.9 used quite a bit. But I know that section 5.2, that method is used as well. But it's, you know, okay, all right. Okay, I understand. I understand where you're coming from, Mikkel. I do, I do. All right, how many think like this is really quite beautiful? Okay, Kevin loves it, and Christy, wow, a lot of people. Sega, Diva, Ryan, we're getting a lot of positive responses here. That's great. That's great. Great. James, great. All right, let me stop the recording.